All right, so let's remind ourselves where we were in 3.4 since it's been, a bit since we looked at it. So we're looking in 3.4 at concavity. Concavity talks about the shape of a graph, not how the graph is changing, but how its derivative is actually changing. And we also talked real quickly about the second derivative test. And the second derivative test still tells us about maximum and minimum values. So we talked about that if our derivative is increasing, then we have a graph that's concave up. It also means the second derivative is positive. And if our derivative is decreasing, then our second derivative is negative and we have a concave down graph. And this one actually wrote it out in a slightly different way, but they said the same thing. So second derivative positive, it's concave up. Second derivative, it's negative, it's concave down. So we had taken this example where we took the derivative and then the second derivative, and then we set the second derivative equal to 0, and we created that same sign chart that we've been doing before, but with the second derivative's locations instead. And if we ended up putting the test point values in and we got a positive for the second derivative, it was concave up. And if we got a negative for the second derivative, it was concave down. So shake your head if that's sort of sounding somewhat familiar. Okay, we're going to do some more examples of that. Inflection points. So an inflection point is actually a place where you're changing concavity. So more specifically, suppose we have a continuous function on an interval AB. The graph changes concavity at a point C within the interval, right? So it changes from being concave up to concave down or vice versa. And when it does do that, it's called the inflection point. Okay, so the inflection point is the place where it looks like it stops being upward curving or cupping and to being lower, right? It turned to being upside down kind of parabola shape. So in particular, if we had a graph that looked something like that, visually speaking, it would be somewhere in between those locations where you see the cupping up here and it opening downward here. So this would be what we would visually refer to as the inflection point. Now, very specifically over here where we did this, there are inflection points that we can find very concretely, and they would be these locations, the places where it stopped being one and started being the other one specifically. Now, those are only the x values of it, right? How would we find the corresponding point if I knew the x value? Plug it into what? The original equation, right? So you'd find the corresponding output value by using the original equation. All right, so we're going to take a look at that kind of information. One more theorem before we do. Theorem 3.8 talks about points of inflection. So if C, f of C is a point of inflection, either the second derivative is equal to 0 or the second derivative does not exist. So we could have those locations where the original function existed, but the second derivative didn't. And we saw an example of that happen, I can't remember if it was in 3.3 or if, I think it was in section 3.3, where I ended up with a vertical tangent line. Do you remember that? And where I had it was a first derivative in that location, where I had a vertical tangent line. Well, the second derivative wouldn't exist, but it could still be a place where the concavity changed. And in particular, the graph, if you remember it, that's not good. The graph looked something like this. It looked more straight than that in the middle. But this location right here, if I compact it a little bit more time, let me see if I can actually shrink it to do that. No, I can't. Let's try it again. That's a little bit better. This point right here had a location where I had a vertical tangent line. So the derivative didn't exist, and we had problems with finding the derivative as such. But you can see that this is a point of inflection visually, right? Mm-hmm. Yeah. So we can still have an inflection point even if the second derivative doesn't exist at that particular location. That still is a possibility. We need the original equation to exist at that point, but not necessarily the second derivative. All right, so here's an example of one we're going to do. We're going to find the points of inflection, and we're going to discuss the concavity. So this is very much like the last question that we did, where we're finding the second derivative, setting it equal to 0. It's just got this extra little piece in the directions about finding the points of inflection as well. So not a whole lot different. You can do a couple of things. If you really want to multiply it all out, you could. It's not terribly, horribly ugly, right? It's just cubed. But we also have at our disposal product rules and chain rules, so we don't have to multiply it out. So I'm going to avoid multiplying it out since we have a little bit more advanced tools at our disposal that we don't need to. So we're going to take our derivative And as we take our derivative, you'll remember the first one gets rewritten, and then we need the derivative of the second. So here's my two pieces. So the derivative of a part that's underlined second would be that we bring the 3 down, we rewrite the inside to the 1 power less, and then the derivative of the inside is 1. Okay? Hopefully all of that is still ingrained enough after the quizzes that you guys did that even though we took a break, we're still okay with that. The other half is easier, so the derivative would be to rewrite the first piece, or to take the derivative of the first piece and to rewrite the second one. So x minus 4 cubed. Okay, so this is my first derivative. You might still here be tempted to go ahead and multiply it out. I would at least be tempted to clean something up before I go, like smoke and rot through to take the second derivative. This is really, there's no reason to leave it this messy to take your second derivative from here. So in particular, some of the things that you might kind of notice is that these each have this x minus 4 in them, right? One of them is power 2 and one of them is power 3. Agreed? Mm-hmm. So I could factor 2 of those, right? That with the power 2 out in front of the whole thing. And that's what I'm going to do. I'm going to rewrite this so that I have x minus 4 squared out in front. And if I do that, then I'm going to have these 2 pieces left, so that's 3x. And I'm going to have one of these left. So that's plus x minus 4. Is that okay? Those are the pieces that remain after I factor out the x minus 4 squared. And there's really no reason not to clean up one tiny little bit more. And that would be to recognize that this is 4x minus 4. Okay, so far so good? There's a typo in there unless I've got something else. I think we're okay. I think I just have a typo in my notes on here, but that's fine. Okay, everybody good? Awesome. All right, so from here we can take a second derivative pretty nicely because it's in a very condensed kind of form. So we'll rewrite the first piece. Take the derivative of the second one is just a 4. Taking the derivative of the first one brings the 2 down. Rewrite x minus 4. Now it'd be to the power 1 times 1. And then times the second one as is 4x minus 4. As we're working our way through, you might be sitting here thinking, I think it'd just have been easier to cube the thing to begin with. And you might be right. We're going to end up being, multiplying and condensing some things as we go still. But there's a lot of pieces here. We could do the same thing we did on the last one, whereas we recognized that this x minus 4 is in both those pieces, and I could pull it out to the front. So we could do that if we recognize that. So I have x minus 4 one of the times, because there's only in there twice on the first one and once on the second one. If I do, I have the same x minus 4 times 4 left here, so that would be 4x minus 16. And then over here, I have the 2 and I have the 4x minus 4. So that would be plus 8x minus 8. Did you get all those pieces? This one and this one right here.
Oh, okay.
Yeah, I think we have 8x minus 8. Does that look all right? Okay. And with this one, I can't rely on my notes because I made a mistake somewhere along the way in there. So I have, let's see, that's 12x and then minus 24. That's divisible by 12, so if you want, you could factor a 12 out. So we've got x minus 4 and then x minus 2. That's not too bad. Setting that equal to 0 is very nice, right? So if I set this equal to 0, what are my two x values that I get?
4.
4 and 2. So in terms of a sign chart, those are the two values that are going to be on my sign chart. Let me shrink this a little bit and I'll put the sign chart at the bottom. So on my sign chart, I have 2 and I have 4 and I need values in between. I'm going to pick 0, 3, and 5. Does that work? Okay. We're talking about concavity here. So when we're talking about concavity, we need to know what happens to the second derivative. So these locations where I just have the 0, the 3, and the 5 that I'm putting it in, You're welcome to grab a calculator. You're welcome to put it into any version of the second derivative you want. So whatever second derivative piece you like, it doesn't really matter. You're going to put it into any of them that you wish. And you're trying to find out what happens when I put those values in. I kind of like putting it in the factored one down here. If I put in 0 here, this piece is negative and this piece is negative, right? So I have a positive times a negative, which gives me a positive. So it had a positive on the first one. Did somebody say it wrong? It's all right, it happens. It is early. All right, 3. So the 12 is always going to be positive with the reading. So let's put the 3 in. So the 3 would give me a negative here in the x minus 4 position, but it would give me a positive here, right? So if I plug the number 3 into this, I should be getting a negative. And then if I put the number 5 in, I should end up with 5 minus 4 is positive, 5 minus 2 is positive. It's all positives, so I have another positive. And again, what did this tell me? Well, concave up means it opens upward. The negative, concave down, means it opens downward, and the positive means it opens up again. So in terms of concavity, we can answer that question right away. And not only that, but because we see the changing between positive and negative, the concavity swapping places, right? We actually see inflection points happening here and here as well. So this asked me for 2 things. It asked me about inflection points, and it asked me about concavity. I can answer the concavity directly because I already have a sign chart that answers it for me. So concavity, it's concave up on the positive pieces, so from negative infinity to 2. And then it stops, jumps over here to 4, and then from 4 to infinity. And it's concave down between, so from 2 to 4. Is that all right? There's my concavity. I do have 2 inflection points. I have the inflection point at 2 something and an inflection point at 4 something. Don't inadvertently just create a 0.24. That's not it, right? They're both x values. At 2 and at 4. And how do I find the corresponding output values for each of those? The original equation. Now when I plug in the number 4, that one's the easy one. What do I get? I get 0. So 4 gives me 0. 2 have to work a little bit harder to get. So if I plug in 2, I don't have a calculator with me today, I'm so sorry. So if I plug in 2, what do I get? Somebody tell me. Negative 16? Is that what you said? Do I have a confirmation on that from someone? Okay, we're just going to take your word for it. Awesome. Okay.
Yeah, that was right. I was thinking of the next one.
That's okay. So it works,
Yeah,
Joel?
that's right.
Okay. So we have 2 inflection points, 2 negative 16, and 4 0, and then we have our concavity. I think that's all it asked me for, right? Discuss the concavity, which we did by stating over here. And then we have our points of inflection. So those are the 2 pieces.
I have a question.
Yeah.
Aren't they possible points of inflection? Like, don't we have to check?
They are possible points of inflection, but the fact that they changed right here means that they for sure are.
Okay.
So inflection points simply mean the concavity changed. Now, it's possible when we do our sign chart down here that this is positive and then it's positive again. So while that's a possible point of inflection, like let's say that at the number 2, it actually went from positive to positive, it would be a possible point of inflection, but it didn't actually work, right?
Okay.
So if you imagine a graph
so when
that...
our x equals 4 and 2, those are possible points of inflection. And then when we actually check it down here is when we
Yes.
actually confirm that they're...
Correct. So at this point, we have a possible points of inflection, and at this point, when we've done our sign chart underneath it, then we've found that they for sure are.
Okay.
Yes,
okay.
you're right. There's a graph that does this, where it looks like a W shape.
Mm-hmm.
So this would be a really good example of where we have different locations where the derivatives exist and don't exist and so forth, and have derivatives of 0, but it would be concave up on both pieces.
Mm-hmm.
And so this point in the middle where it comes up to a peak would be a possible point of inflection, but it wouldn't actually work. And it would find that out by doing the sign chart.
Okay.
Yeah.
I gotcha.
Okay. So the second derivative test we alluded to last time, but I didn't actually discuss it directly, at least not with the theorem. So Theorem 3.9 talks about what the second derivative test actually does for us. So these locations where we have a second derivative that is negative or a second derivative that is positive create concavity that's up or down. We knew that already. But the reality is that those locations, the C, so right, oops, I meant that to be a highlighter. Let's try that again. So let f be a function such that the derivative f of x equals 0, f prime of x equals 0, and the second derivative of f exists on an open interval containing c. I think that needs to say f prime of c equals 0 for this to make sense. Change that in your notes for me, please. F prime of c equals 0. So the derivative location, right, it's a critical point, in other words, right? C is a critical point. Well, if c is a critical point of your equation, and you actually find out that the second derivative is negative there, then you have an absolute minimum, or a local or relative minimum point. And if you find out that the derivative is, I said that wrong, maximum there, if it's negative. And if the second derivative is positive, then it's going to be opening up. You have a local minimum there. So this is telling us, remember again, that the negative means it's opening downwards, and this is that it's opening upwards. But we also know from the description, because C is a critical point, that its derivative is actually 0. So we're actually finding whether it's a max or a min at that location, because we're talking about this specific point that's happening here, not just the interval as a whole. So you can actually use the second derivative test to do this, just like we used the first derivative test with a sign chart. The interesting thing about the second derivative test is that there's no sign chart necessary. So let me show you how this works, because I've shown you a picture where it looks like it would be. We've got an equation, f of x equals x squared plus 1 over x, and our directions are to find the relative extrema, and then it specifically says to use the second derivative test. Okay? So anytime we're talking about second derivative tests, we're going to need the second derivative. So the beginning of this looks just like the previous problems that I worked. We're going to take our first derivative, we're going to clean things up a little bit, we're going to take our second derivative. So that's where we're going to start. So this is a quotient rule, yeah? Okay, so for a quotient rule, we have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. Got another error in my notes. That's good. Evidently, this notes needs a little bit of work. All over the denominator squared, yes. Okay. So we want to clean that up because that's messy. That's 2x squared. And then minus x squared and minus 1 over x squared. And I believe we've got that simplifying. Just make sure I didn't make any mistakes. What was that?
X squared, right? On the top, we make it x squared minus 1.
Right, x squared minus 1 over the x squared. Is everybody good with the first derivative? The nice thing is the first derivative is not that much different looking than the original equation, so finding its second derivative is not going to be that much different. So we'll find the second derivative now. So we have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. Yes, ma'am.
To make it easier, could you just do 1 minus x to the negative 2? Or no?
So I think you're asking if you could rewrite this differently. So you can rewrite it. I'm not so much sure that it makes it easier. And the reason I'm not so much sure about that is because you would then have a product rule.
No, what I'm saying is because
Oh, so you mean to rewrite it like two fractions where you're dividing each piece?
Yeah.
You could. Again, I'm not sure that it's going to make it any easier. It's not wrong. So you're thinking writing it like that?
Yeah.
You could. Because the reason I'm saying I'm not sure it's going to make it any easier is because eventually you're going to have to set it equal to 0 and you're going to have to take it out of its form that it's in a negative exponents anyway. You can certainly do it. I don't think it's going to make it any harder. But I don't think it's going to condense it that much either. So,
Okay.
But you're welcome to try to do it that way. You'll get the same answer.
Okay.
So, yeah. All right. The nice thing about this particular numerator, if we do it from the quotient rule, is a lot of the things cancel out. So I have 2x cubed now. I have minus a 2x cubed. And then I'll have plus 2x. Does that look right? Over x to the fourth. So these pieces cancel, and I end up with 2x over x to the fourth, which will also reduce to 2 over x cubed. Is that okay? Everybody good? Okay, cool. All right, so let's come back up for a moment to where my derivative, I've got all the highlighting over here from the question we were looking at, but this piece right here, we need to find the critical points, right? That's the whole point of this particular question, is to find out where I have maximum and minimum values, and that's only going to happen at either places where I have derivatives equal to 0 or derivatives not existing. So when does this piece, let me take this part out here, when does this equal 0 or does not exist?
It doesn't exist.
And 1, 0.
Okay, 1, 0, there's one more.
Negative one.
-1. So if I had my numerator set equal to 0, I would have x equals 1 and -1, right? And if my denominator is equal to 0, x is equal to 0. Everybody good so far? Okay. The denominator when x is equal to 0, that piece right there is not going to give me a local max or min. Why not?
Because it doesn't exist.
Okay, so it doesn't exist. What's happening on the graph at x equals 0? There's an asymptote. So the original equation itself, where x is equal to 0, is that I have an asymptote. Okay, is everybody good with that? So yeah, I mean, I can set the derivative equal to 0, and x equals 0 comes out of that as a potential location of a max or min, but it's not going to be a max or a min because there's an asymptote there from the original graph that we know about. So I don't really have this x equals 0 happening as part of a potential max or min location because there's an asymptote. I just have the x equals 1 and x equals -1. So why does this matter? Well, these two locations are the C's that it's talking about here. Okay, those are the places where I'm going to have potentially, have a local max or a local min. And the way that I can use my second derivative to find it is that I actually just take my second derivative and I evaluate it at those locations. So I take my second derivative and I evaluate it at -1. And I take my second derivative, I evaluate it at +1. So I'm not getting intervals of concavity here. That's not my question. My question is asking about maxes and mins, right? It says find relative extrema using the second derivative test. So my second derivative test means I take my second derivative, and it means I take the critical points from the first derivative, 1 and -1, and I evaluate it into the second derivative. So when I put 1 into 2 over x, 2 over 1 cubed, what I want to know is, do I get a positive or a negative? I get a positive. And when I put in the -1, what do I get? Oh, I wrote them on the wrong spots. I'm sorry. I just got them backwards. I should have switched them in the other spot. That'll work. I get a negative, right? So when I plug in -1, I get a negative. When I plug in +1, I get a positive. What does that mean? Well, if the second derivative is negative, it means that it's concave down. And if the second derivative is positive, it means it's concave up. And that's true. I mean, I do have that information about the concavity at those specific points, not an interval, but at those specific points. But because it's a critical value, right, the derivative is equal to 0, and it's concave down. Let me draw my picture. This means that I have a max. And since x is 1 is a critical point and it's concave up, it means that I have a min. So what I actually found out without doing a sign chart is I found out that I have a max at -1 something. We'll figure it out in a second. And I have a minimum at 1 something. And I didn't find it out with a sign chart. I found it out with a second derivative instead. So I just need the corresponding output values, and I can get that from the original equation. So if I plug in -1 into the original equation right here, I need an actual value now, not a sign. So what do I get? -2. And if I plug in 1, I get 2. So I have a max at -1, -2, and I have a min at 1, 2. So far, so good? Okay, it's a second way of doing the same thing, identifying whether I have a maximum minimum value, just not with the sign chart in the first derivative, but with the second derivative. All right, same directions. We're going to do a trig function one, and obviously anytime we work with trig functions, they give us an interval to work on. Otherwise, we have these unlimited peaks and valleys going on for at least our sines and cosine graphs. You might notice that this interval is a little different. Do you have any idea from trig or a pre-calc class or something like that you've had, why do you suppose they're having your interval go from 0 to 4 pi on this particular equation?
Because you're like taking x divided by 2, it's not just x.
Yeah, the inside of my sine actually is division by 2. So it's taking that interval, which was 0 to 4 pi, and it's halving it. So I really do have an interval that's a full period, right? Like that's really what's going on. That's why I'm allowed to have a longer interval here, and it makes sense from that same perspective. If that doesn't resonate with you, it's not a big deal. But I just want you to know there is a reason they chose 0 to 4 pi here. It's not arbitrary. All right, same things as we did before. We're going to take our first derivative. We need to know what the critical points are. We're going to take our second derivative, and we're going to use it to evaluate our points from our first derivative's critical points. So, for starters, our derivative. So what is the derivative of sine of x over 2?
Cosine x over 2 times 1/2.
All right, so cosine of x over 2, that's the derivative of the outside. And the derivative of the x over 2 is 1/2. I'm just going to write it in front. I don't want to accidentally think that I'm going to multiply my 1/2 and my x over 2 because I'm not. Okay, so that's my first derivative. It's really nice because I don't really have to do a whole lot with it, right? No cleaning up. So this one's pretty friendly. We'll set this equal to 0 in a moment. Trig functions, at least sines and cosines, don't have to be not equal. They don't have to have a set equal to does not exist. That doesn't happen. It's just the equal 0. So we'll come back to that in a second. Since we're in the mode of finding a derivative, let's continue. So what's the derivative of 1/2 cosine of x over 2? Okay, so negative 1/2, I'm going to write it out just like you said, sine of x over 2, and then times 1/2 again. So I'm going to end up getting negative 1/4 sine of x over 2. Is that okay? Cool. All right, coming back up here to this, where in the world does the cosine value of x over 2 equal to 0? Notice I'm kind of ignoring the 1/2 at the beginning because it's irrelevant. If I multiply both sides by 2, it will go away. So as I think about solving this, and we'll write it out just a little bit more clearly than I did maybe on the last one because it's a little bit easier to work with that way, I think. So if I multiplied by 2, I'd have this equation. Where does cosine on my unit circle equal 0? Ignoring the x over 2 part now. For what was it? Okay, so cosine at pi over 2 and at 3 pi over 2. Do you guys agree? That's where the cosine values are equal. Okay, good. So my cosine of pi over 2, or of x over 2, equals 0 when x over 2 is equal to pi over 2 and 3 pi over 2. But I have a problem. Close. But I will do that, but I'm not there yet. You're right. What was my interval? 4 pi. Which means, so far, all I've done is to go around my unit circle one time. That's 0 to 2 pi.
We have to do it again.
We have to go around again.
So we need
So not only is pi over 2 and 3 pi over 2, but I also need 5 and 7. So 5 pi over 2 and 7 pi over 2. And the reason I do is because I have to go around twice. Right, I'm supposed to get all of those points. And then I'm going to multiply by 2, just like you guys suggested, which is, of course, going to eliminate all those denominators. So the x values themselves are going to be at pi, 3 pi, 5 pi, and 7 pi. And it would keep going, right? I mean, like it doesn't stop. We are going to have to, examine whether or not these are within the interval that I need at the end. Obviously, some of them aren't, but we want to be a little bit careful along the way. So I have all those values plus more. I mean, it continues. And I want to test those inside of here. But I only need the ones that are between 0 and 4 pi, which actually ends up still being the first two. So on this one, it doesn't always work this way, but on this one, if I had forgotten to continue to go around my circle, it wouldn't have hurt anything. I would have still gotten the same 2 original points between the 0 and the 4 pi. So these 2 locations are going to be evaluated inside of my second derivative. So I'm going to take my second derivative at pi and my second derivative at 3 pi. And I don't need to go to the 5 pi and the 7 pi because they are now outside of my interval 0 to 4 pi. And I'm trying to figure out what happens when I plug them in here, right? So what in the world do I get when I take negative 1/4, it's negative first of all, negative 1/4 sine of, and it's pi over 2 now. And if I do negative 1/4 sine of 3 pi over 2, and again, what I want to know is I want to know the sine. So say again. So I want to know the sign on the. Are you doing the first one?
Yeah.
Okay, so if I put the negative, or if I put the pi in, sine of pi over 2 puts me at the top of the circle, right? And the sine value there for is positive, right? Times the negative in front, so it should be a negative. Is that what we're getting? Okay. And then if I'm at 3 pi over 2, I'm down on the bottom of my unit circle, which means my sine value is negative, but the negative 1/4 at the beginning is going to make it positive. So negative means it's concave down, which means I have a max. Positive means it's concave up, which means I have a min. That's what the second derivative test does for me. Okay, so it would probably be really good for you to highlight this statement that says second derivative test somewhere and to make yourself a note, because this is a really common mistake for students on the test. Whenever it says second derivative test, it means you have no sign charts. So if you have a sign chart present and you're being asked to do a second derivative test, you're using the wrong test. Okay, it's like a red flag kind of thing. Second derivative test means there's no sign charts. It means you're evaluating into the second derivative. So we have what did I do? I have max at pi something, and I have a min at 3 pi something. How do I find out the y values that correspond? Original equation. So if I do sine of pi over 2, what do I get? I get 1. That's my max. And if I have sine of 3 pi over 2, I get negative 1. And it should make sense as you're looking at that and you're thinking, well, yes, I mean, if this is the value of 1, that is, 1, that's the maximum value on a sine graph, right? That makes sense. And a negative 1 here is a minimum value on a sine graph. So it should resonate with what you know about trig functions to begin with. Any questions on that?